right, well, in this lecture video, I'm going to walk you through a couple of different methods for doing interpolation. Let me grab my pen here. Hopefully I can write legibly enough for you to see what we're doing. So we're continuing on in section what I called 5.4, which is the Lagrange form of the interpolating polynomial. Remember, we're again trying to consider the case where we have x naught. So actually, let's do x in y. Actually, no, let's do x I to yi. Let's take a set of these guys. I equals 0 to n. Okay, again, this looks like a bunch of points, right? So we've got, here's our x0, here's our x1, here's dot dot dot, here's our xn. We're trying to find a curve that passes through all of these points, right? Boom, 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 boom. Okay, so let's write that down. Our goal, find an nth. Is it nth? How many degrees do we need? Nth degree. Yep. Actually, it's if we have n plus 1 points, right, then we need nth degree. Yep, polynomial such that p of xi equals yi for I goes from 0, 1 all the way up to n. Okay, given that, now the question is, how do we find this? Remember, we've already considered the direct method. Okay, now what we're going to do is we're going to use the Lagrange method. Now, the Lagrange method is kind of sneaky in the sense that what the Lagrange method allows us to do is basically say, let's invent a set of polynomials. We're going to call them cardinal polynomials. Okay, so let me write that down. Cardinal polynomials, which are going to be in this form. They're going to be L sub I of x, okay, where I again goes from 0 up to n, okay, and these are all of degree n. Okay, with the following property. In order for them to be cardinal polynomials, they have the following property, such that if you take Li, that is the ith cardinal polynomial, and plug in the jth point, x sub j, you're going to get one of two things. Okay, you're going to get 0 anytime I is not equal to j. So say I took the right here, this was 1 and this one was a 2, L1 of x2 would have to be 0. Anytime those two are not equal, we want the output of that polynomial to be 0. Otherwise, that is, any time that they are the same, we want it to be equal to 1. Now, what's so creative or sneaky about these polynomials? Well, I'll show you. Okay. What happens now is this means that p sub n, that is the polynomial we're looking for. In fact, I don't even need the n in there. I just called it p. The p that we're looking for, I can write down immediately now. It's going to be the sum from I equals 0 to n of Li of x times yi. Oh, get out of my way. Sorry about that. Okay, this is my polynomial. I'm actually done. Okay, that's on the condition that I can find out what these guys right here are. But the question is, what do those really actually look like? But this is a polynomial that satisfies my original conditions. Remember, my original goal was that p at x I, and let me be careful now. I probably could do this. I'm going to say j needs to be yj. I put j in there because up here I put an I in my formula, and I wanted to make sure that you're not confused between that formula that has the I and the indices of the sum and the one down here. All right, so let's see, why is that true. Why does this work? So the question now is, why is this going to work for us? And the answer has to do with the fact of how we define that Li of x. Remember, what we want here is this guy right here to be true. I'm sorry you can't see the cursor whenever I'm waving it around here, so I have to underline whenever I'm talking. But the point now is, what does P of xj look like according to this definition that's up here? Okay. Well, according to that, if I plug in xj, that means I'm going to stick in right here. I'll put this in red. This right here, xj. Okay. So P of xj is the sum from I equals 0 to n of Li of xj yi. Now remember, what this looks like is this. We're summing over I, right? So this would be like L1 of xj y1 plus L2 of xj y2 plus all the way out 2. And at some point, what's going to happen is you're going to have an Lj of xj yj, and you're going to keep going, and you're going to get all the way to the end, Ln of xj yn. Now, why did I put all these terms in here? Well, you remember that L1 xj, as long as j is not 1, that right there is 0. In fact, all of these polynomials are defined to be 0 whenever the two indices don't match. But when they do match, so if you have a j here and a j here, since they match, then that's going to become a 1. This becomes yj, because all of these terms cross out and become 0, and the only term you have left is this term right here, which is 1 times yj, and now you have P of xj equals yj, which is exactly what our goal was right there. Now the question is, what do these polynomials look like? That is, what does this guy right here look like? So that the original condition that we had is true. That is the condition, if I go back up here, this condition, I went too far. This condition right here has to be true. We know it's a polynomial. In fact, that's what I called it. I called it some kind of cardinal polynomial right there. But what does that polynomial look like? Well, with, again, a little bit of creativity, we can make that work. And I can show you what those polynomials look like. Okay? So let's write that down. What do the cardinal polynomials look like? Okay, well, let's go ahead and write it down. In fact, I'm just going to write it out in its full form so you can get the idea. Li of x looks like this. If you take x minus x naught divided by xi, where I is the index of whichever cardinal polynomial you're looking at, minus x naught, right? That's, by the way, a linear polynomial right there. If I take another term, I'm going to do x minus x1, that's a 1, not an I, divided by xi minus x1. And I'd keep going, just like that. So the next one would be x minus x2 over xi minus x2. Well, eventually I'm going to get to the term that's right before I. So I'm going to do x minus x sub I, that's I, minus 1 over x sub I minus x sub I minus 1. There's another I there. Times, and now skip the one with the I in it, because if I did xi minus xi on bottom, I would get divided by 0. So x minus xi plus 1 divided by xi minus xi plus 1. And then you keep going all the way to the very end, so you have x minus xn over xi minus xn. Just like that. Now, what degree polynomial is this? Okay, count how many x's you have. You have 1, 2. Now, how do we have we gotten to when we get to this point? We have I minus 2 at this point, right? Because it's 1 less than whatever index I'm on. This one, the first one right here had a 0. So it's actually 1 more than that. I should say I got to I. This one is 1, I've got 2. So this is, I've gotten to I. Now this one, since it's the very next one, it's I plus 1. Now from this point on, it's going to match. Notice again, I skipped the pattern right here. So there's not actually an I here. So the next one after that's I plus 1, which from that point on, it's going to match the index. So I have n. So it's nth degree polynomial. Okay, now check this out. What happens if I do Li of xi? Plug in an xi. I claim that equals 1. Isn't it? Just check it out. If you plug in an xi here, 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 the numerators and the denominators look the same all the way out, and so you end up with 1. Boom, exactly what we want. Now what happens if I do Li of xj, and again I not equal to j? What happens there? Well, since the one term that we skipped was when they were the same, somewhere in here the term is 0, right? Because you'll have an xj minus xj over xi minus xj. When you plug it into all these yellow x's up here, one of those is going to be 0. And so when you multiply by something that's 0, that term is going to be 0. So you end up with 0, which is exactly the condition that we want. All right, now to get a better feel for what we're talking about here, let's do an example. All right, so let's take a look at an example. Our example is we want to write out the cardinal polynomials appropriate to the problem of interpolation, or of interpolating the following table. And we're going to give the Lagrange form of the interpolating polynomial. So here, let's draw our table. So I have a row for the x's, a row for the y's. So these are going to be my inputs and my outputs. So I want, if x is 1/3, I want x, or so the output of my function, of my polynomial, will be 2. If x is 1/4, I want the output to be -1. And for x equals 1, let's have an output of 7. So in order to do this, remember, we're going to do this using the Lagrange form of the interpolating polynomial. We know that if you have x0, x1, x2, we're going to have the output we want to be y0, y1, y2. And we know since n is 2, we need quadratic, and we need these L's. So we're looking for the cardinal polynomials L0, L1, and L2. And our polynomial will look like this. It's going to be y sub 0, L0, plus y sub 1, L1, plus y sub 2, L2. Where, again, all of these L's depend on x. These are the cardinal polynomials. So let's start with L0. L0 of x, we're going to, remember, plug in x minus x1 on top and x0 minus x1 on bottom. So we skip the x0 column, but that's what's going to be in the denominator. So we get on top x minus x1, which is x minus 1/4, over x0 minus x1, which is going to be 1/3 minus 1/4. Now we go on to our x2. So on top we're going to have x minus x2, which is going to be x minus 1, over x0, which is 1/3, minus x2, which is 1. So 1/3 minus 1. So let's simplify this just a little bit. If we take 1/3 minus 1/4, that's going to be 4/12 minus 3/12, right? which gives me 1/12, because you get 4 on top minus 3 on top over the common denominator is 12. 1/3 minus 1 is negative 2/3. If we multiply those two together, the 2 cancels with the 12, leaving me a 6 in the denominator. So that's going to be negative 1/18. Divide by negative 1/18 is to multiply by negative 18. So we're at a negative 18, and then we'll still have the numerators, which is x minus 1/4 times x minus 1. All right, let's move on. L1 now. Going back to, our form for the interpolating polynomial, the cardinal polynomials. You can go back and look at your notes earlier. We're going to use and skip, actually, the column for the numerator, meaning we start with x minus 1/3 over 1/4 minus 1/3. But we're not going to put the x minus 1/4 factor in there. We skip over to the x minus 1 factor. So x minus x2, which is x minus 1, over 1/4 minus 1. So that's going to give me, on bottom here, that's now negative 1/12. And 1/4 minus 1 is negative 3/4. 3 divided into 12 gives me 4. So I end up with a positive 1/16. To divide by a positive 1/16 is to multiply by 16 over 1. So I got just 16 out front, and then x minus 1/3 times x minus 1. Now let's do L2. Following the same pattern, we're now going to have x minus 1/3 on top. That's x minus x0. And then on bottom, x2, now minus x0. So that's 1 minus 1/3 times. Now we're going to do x minus x1 on top. So x minus 1/4 over x2 minus x1, which is 1 minus 1/4. That gives me, on bottom over here, I've got a 1 minus 1/3, which is negative 2/3. Oops, hold on a sec. Grab my pen back here. 1 minus 1/3, negative 2/3. Sorry, having a little bit of technical difficulties here. I'll write this in just a second. Hold on. And so 1 minus 1/3 is negative 2/3. Oh, positive. I keep saying negative, positive. And then 1 minus 1/4 is positive 3/4. That gives me 1/2 when I multiply it out. So I have 2. Because I divide by half, it's multiplying by 2. X minus 1/3, x minus 4. All right. Now let's plug that into P of x. All right, so now we've got all of those. We can write out our Lagrange form for our polynomial. Let me scroll it down just a little bit so you can see it all. All right, so what do we got? We'll have that P of x is, now you got to remember the values. You've got them written down. I'm going to pull them up. Y0 is 2, so you'll have 2 times L0, which is a negative 18 times x minus 1 over 4 times x minus 1. And then you've got plus, and then you've got a negative 1 times the 16, x minus 1/3 times x minus 1. That's up here, times L1. And now also add y2, which was just a 7. So 7 times 2 times x minus 1 over 3 times x minus 4. So I'm going to write it out just a little bit simpler, but I'm not going to multiply out all these fractions. You end up with just negative 36 x minus 1/4 times x minus 1 minus 16 times x minus 1/3 x minus 1, and plus 7 times, no, not 7, 14 x minus 1/3 x minus 4. Now this process gives you the interpolating polynomial. Unfortunately, it gives you a very long form for it, and it takes a lot of multiplications and operations to actually evaluate this polynomial in general. But we found it. We can now find a polynomial that passes through any set of points. Okay. If you go back to what we were covering at the very end of class on Tuesday, I gave you a theorem, and the theorem basically said that this interpolating polynomial exists. Okay. I gave you this theorem that had this notation in it. Okay. Interpolating polynomials exist and are unique. Now, I'm not going to write out the proof just because I don't think it's optimal for this delivery style, but I'm going to suggest to you that we proved unique in class. This Lagrange form basically proves that it exists. Right? We found earlier, in fact, I can just go up in my notes. I'm going to scroll back up here. We found that if we defined cardinal polynomials, and we could find a polynomial that meets this criteria, and we wrote the interpolating polynomial like this, right here, then the goal was met. We proved it. That's basically the proof. The proof is that since we can always write down the cardinal polynomials for any list of points, as long as the x's are distinct, then you can write down an interpolating polynomial. And this form right here, this long guy right here from your notes before, that shows you that you can always create an interpolating polynomial, meaning it meets this criteria that's right here. Done. We now know the Lagrange form. Now, is that the best form for the polynomial? And the answer is actually no. By all means, no. There is a much better form, and that's what we're going to cover in the next section. Even though it's going to be an earlier number, this is the next section. So your homework for this class that I'm missing is going to be posted in Blackboard, and it's going to be just over finding the Lagrange form for polynomials. And in class on Thursday, we are going to come back and we are going to find the better way of finding the interpolating polynomial. So you have some work to do with your Lagrange polynomials. If you have any questions, be sure you go check out the textbook. Again, this is section 5.4.